In Chapter 28, we're now going to talk about the chi-square test of independence. This test is used to answer the question of, do two variables affect each other? So for example, let's say we want to know if gender and handedness being if you're right-handed, left-handed, or ambidextrous. We want to see if those two variables affect each other. So in other words, we might be asking something like, is the distribution of handedness the same for men and women? And when I say the distribution just means, are the percentages of right-handed people the same for men and women? What about the percentages for the left-handed people? Is that the same for men and women? The same for ambidextrous? Is that the same for men and women? Now, if the data was available for every man and woman in the population, we could just look at the percentages and answer the question. But we're not going to have the data for every man and woman, because that would be the entire population. It takes too much time to get all the information for everyone on the population. But what we do have is we do have a sample of 2,237 Americans aged 25 to 34. And in this sample, there were 934 men that were right-handed, but there were 1,070 men or women that were right-handed. So these are our counts. These are the actual numbers of people in each category. And then in this table, I put the percentages. So we can see that 87.5% of men were right-handed, but 91.5% of women were right-handed. And so the percentages for each category aren't the same for the women and men. But are these differences just due to our chance error, or is there really some underlying difference between the handedness and the gender? So once again, we can look at it and we can see, oh, women are more likely to be right-handed than men in this sample. Okay. Now, does that mean that women really are more likely to be right-handed than men in the entire population? Or are those differences just due to chance error? Because even if the distributions were the same for the populations, the distributions in the samples could still be different. Okay. Just by the luck of the draw, there could be too few right-handed men in the sample. And so to see if our observed difference is real, if gender really affects your handedness, or if it's just due to chance error, we need a statistical test. The test we use is called the chi-square test for independence. We use this test if we want to know if two variables are independent, i.e. if they affect each other. Well, sorry, independent means that they don't affect each other, and so we're wondering whether or not they do affect each other. And also, just like the chi-square test for goodness of fit, each of the expected frequencies needs to be at least 5 to make sure we have a big enough sample size to use this test. Now, the null hypothesis will always be that the two variables are independent, meaning that they don't affect each other. The alternative hypothesis is that the two variables are not independent, so they do affect each other. And it will always be that way. The no will always be that they don't affect each other. The alternative will always be that they do. Then our test statistic is chi-squared equals the sum of the observed value minus expected squared over expected. Now you might notice that this is the same test statistic as the chi-square test for goodness of fit. The tests are slightly different. The tables are also set up slightly differently. But luckily for us, the chi-square test statistic is exactly the same. Now the degrees of freedom is going to be your number of rows minus 1 times the number of columns minus 1. And when you're doing this, we do not count the headings or totals. Now it's a little bit harder to find the expected values for the chi-square test of independence. What you have to do is each expected frequency or count is going to be the row total times column total over the grand total. So that's the formula you're going to need to know. Once again, the p-value is always going to be the area in the right tail. And we're going to use this to answer questions such as, is handedness independent of sex, or does your gender affect whether you're right-handed or left-handed? Or something like, is income independent of your age, or is your age affecting your income? And is belief in afterlife independent of race, or is your race affecting whether or not you believe in the afterlife? So let's try an example. This is our same example with the gender and the handedness, and we want to see whether or not these two variables affect each other. In this first table, we have the observed frequencies, or counts. This is our actual data. Now in this table, we want to put the expected frequencies. So this is our expected, or our theoretical counts of what we should have had. So what we're going to want to do first is find the expected frequencies. And once again, to find your expected frequencies, you're going to do the row total times the column total divided by the overall total, or the grand total. Notice we have 6 different cells, so you need to do that for each one. So let's start with this first one for men and right-handed. So for men and right-handed, the expected frequency is going to be the row total. So the row total for that row is 2004 times the column total of 1067 over the grand total, overall total is down here in the corner, of 2237. And this gives me 955.8. So we'll go ahead and write that in that cell. Now let's find it for women and right-handedness. So for women and right-handedness, we want this cell right here. So my row total is 2004. My column total is 1170. And my grand total is 2237. This is 1048.1. Now let's do, say, men and left-handed. So that row total is 205 times the column total of 1067 divided by the grand total of 2237. So this is 97.8. Let's now do, say, women and ambidextrous. Let's just skip to that one. So women and ambidextrous, that would be 28 times 1170 over our grand total. So this is going to give me 14.6. And then I'm going to just go ahead and hurry and do the other two with my calculator. So this would be 107.2 and 13.4. Now let's go ahead and start on our actual test. First, notice that all the expected frequencies, so 955, 97, 13, 14, 107, 1048, are at least 5. So the sample size is big enough to do the test. You should always go ahead and check that. Now for our null and alternative hypotheses. The null will always be that your two variables are independent, or that they don't affect each other. So the null here will be that gender and handedness are independent. So they do not affect each other. The alternative is that gender and handedness are dependent, meaning that they do affect each other. Now let's find our test statistic. Remember, our test statistic is chi-squared equals our sum of, we're going to do each observed minus expected squared over the expected. And we have to do that for everything in the table. You'll need to make sure you're nice and organized so that you get everything in. So my first observed is 934 and the expected is 955.8. So it's going to be 934 minus 955.8 squared over 955.8 plus my next one. And you can choose which order you do this in, just be consistent. So I'm going to do 1070 minus 1048.1. And my next value is 113 and the expected is 97.8. And I'm going to go ahead and just write the rest down. So we'll have 92 minus the expected of 107.2 squared over 107.2. Once again, make sure you're dividing by the expected values and not the observed. Plus 20 minus 13.4 squared over 13.4 plus 8 minus 14.6 squared over 14.6. Let's just make sure I was supposed to have 6 of them. 1, 2, 3, 4, 5, 6. Okay, so I think we're good. Now you're going to put this in your calculator. Once again, this does take a long time. Double check it, make sure you're doing it correctly. Chi-squared should be 11.7. Now find your degrees of freedom. Degrees of freedom are equal to your number of rows minus 1 times number of columns minus 1. So come back up. Remember, we don't count the headings, we don't count the totals. So when we say number of rows, there's 1, 2, 3 rows and just 2 columns. So it's going to be 3 minus 1 times 2 minus 1. Because we had 3 rows, 2 columns. So we have 2 degrees of freedom. Now your p-value will always be that area to the right. So here's chi-squared equals 11.7. And on the area to the right, we have 2 degrees of freedom. So 2 degrees of freedom. We want our 11.7, so it's going to be off the chart. So my area is less than 1%. So my p-value is less than 1%. So that is a small p-value, and so we will reject the null hypothesis. So we found evidence that gender and handedness are dependent, or in other words, they affect each other. And now when we say they affect each other, the test just says gender and handedness affect each other. It doesn't say whether gender affects handedness or handedness affects gender, or whether they both affect each other. The test just kind of tests to see whether they affect each other. But logically, we know that it would be gender affecting handedness, since changing from right-handed to left-handed isn't going to make you change your gender. The only way it can work is if what gender you have affects your handedness. Okay, but the test doesn't do that. The test just checks to see if there's any interaction going on. Also, this is my little note here, unfortunately all the chi-square test of independence tells us is whether or not your gender affects your handedness. It doesn't tell us which gender is more likely to be right-handed or left-handed or ambidextrous. Now in our next example, a survey was conducted to evaluate the effectiveness of a new flu vaccine. The vaccine was provided in 2-shot or 1-shot sequences. Some people received 2 shots, others received 1 shot, and others neither. A simple random sample of 1,000 local residents was surveyed. Conduct a hypothesis test to see if the vaccine and the number of shots affects whether people get the flu. So we have 2 tables. The one with the numbers already in it, that would have to be our observed. And then I've given you this other column to put your expected, or the other table. The first step with this test is to find your expected frequencies. And your expected frequency is going to be your row total times your column total over the overall grand total, with our overall grand total being 1,000 because I surveyed 1,000 people. So let's go ahead and find each of these expected values. So let's do this one first. So let's do no vaccine and get flu. So the row total is 46. The column total is 313. And the grand total is 1,000. So this gives me 14.4. Let's try 1 shot and get flu. So 1 shot and get flu, that would be our row total of 46 and our column total of 109 divided by your grand total of 1,000. So 5. And now let's do 2 shots and get flu. So that has a row total of 46 and a column total of 578 over 1,000. This is 26.6. And let's do just one more. Let's do no vaccine and not flu. So that would be 954 times 313 over 1,000. So let's see, 298.6. And I've already done the others. I'm just going to tell you that they are 104 and 551.4. So we have all of our expected values. Now let's just double check. All expected frequencies or counts are at least 5, right? And the smallest one is 5, so we're good. So we can do the test. You should always check that. The null hypothesis is always going to be that they are independent, that they do not affect each other. So the vaccine and whether you get the flu are independent. They do not affect each other. The alternative could be that it has to be, the vaccine and whether you get the flu are dependent. So they do affect each other. Now next, let's find our actual chi-square test statistics. So it's going to be the sum of each observed minus expected squared over the expected. So my first one, my observed is 24 and the expected is 14.4. Squared over 14.4. And notice you're matching up the same spots. So this spot corresponds to that spot. So 9 minus 5 squared over 5 plus, my next spots are 13 and 26.6 squared over 26.6 plus my next spot is 289 and 298 once again, make sure you're dividing by the expected value plus, let's see, 100 minus 104 squared over 104. And our last is we had an expected of 565, sorry, an observed of 565 and an expected of 551.4. So this gives me 17.4. Make sure at this point you try it on your own calculator and then you can get the same answer as I do. Your degrees of freedom are your number of rows minus 1 times number of columns minus 1. So let's go back up and look at this. We have, remember, don't count the totals or the headings, so we just have 2 rows and 1, 2, 3 columns. You'll notice in this class we're never really going to do anything much bigger than like 2 by 3, maybe 2 by 4, because it's going to just take too long to do the problems by hand. And in real life you would get to use a calculator. So we have 2 rows minus 1 times 3 columns minus 1, which gives me 2. So my p-value, here's my 17.4. We want the area to the right, and we have 2 degrees of freedom. So once again, 2 degrees of freedom. We're looking now for 17.4. It's still going to be off here less than 1%. So p-value is less than 1%. So this would be a small p-value, and so we would reject the null hypothesis. And we have evidence now, and lots of evidence, because it looked like that p-value would be pretty small. So we have evidence that getting the vaccine and how many shots and whether you get the flu affect each other. And again, the test doesn't say whether it's the getting the flu affecting the vaccine or the vaccine affecting whether or not you get the flu, or both of them affecting each other. Sometimes you can figure that out by pure logic, sometimes you're not sure, and maybe sometimes it really is that they both affect each other.